So good morning everyone, welcome to lecture 7.1 of our group theory course. This is the first lecture of chapter 7. In chapter 7 we start specific applications of group theory to different aspects of molecular physics or molecular chemistry. For instance, this is the part 3 of our textbook. So in chapter 7 we will deal with electronic states of molecules. In chapter 8 we will discuss vibration, molecular vibrations, and so on and so forth. So let's start chapter 7. Let's start discussing electronic states of molecules and the concept of directed valence. So before we start with the group theory techniques, I just want to remind you of a few very basic aspects of molecular electronic states and molecular chemistry, and the concept of covalent bonding that perhaps you have seen this already in undergraduate molecular physics or even solid state physics courses, or in chemistry is very basic too. So one of the most common methods to investigate the electronic structure of a molecule is to start with an approximation called Lcao, a linear combination of atomic orbitals, in which you expand the wave functions of the molecule in terms of linear combinations of orbitals that are centered in the atoms. Okay. Of course, you can go a long distance with this approximation, but I will basically, for the purpose of introducing the concept, I will basically take the simplest possible case, which is considering the case of, for instance, a hydrogen molecule, or even simpler, H2 plus ion, molecular ion. So 2 protons and 1 electron. And in this case, what I mean by linear combination of atomic orbitals is simply using a basis set of 2. If you are interested in describing, for instance, the ground state of this molecule, you take the 2 ground states of the hydrogen atoms, which are 2 s orbitals, one psi 1 and the other psi 2, centered in atom 1 and atom 2, and you try to construct the molecular states of the molecule as linear combinations of this orbital. And what one typically see when you solve this problem exactly by diagonalizing the Schrödinger equation is that you have 2 solutions. One lower energy solution that is called the bonding state or bonding molecular orbital, and the other higher energy solution, which is the anti-bonding state. And in the bonding orbital you have a symmetric linear combination, and the anti-bonding you have odd or under inversion antisymmetric linear combination of atomic orbitals. Okay, and these are the 2 energy levels that I discussed. What we're gonna see here in this chapter, and it's how group theory can help us simplify this problem by actually telling us what are precisely the symmetries and sometimes even the precise linear combinations of atomic orbitals that are going to be the solutions of the Schrödinger equation, because as we have seen, these must be functions that are basis functions for different representations of the group. Okay, so the idea is, just another example to show that the idea of direct valence or bonding orbitals, in the sense that you accumulate charge in the region between the two atoms, and this is precisely what we call by forming a bond. This also happens in a solid. So this is a picture of the sp3 bonds in silicon. So, and the yellow spheres are the atoms, and the blue regions are accumulation of electronic charge that are precisely directed towards, between two neighbors, between two atoms in a given chemical bond. So going back to group theory will help us in, as I said, identifying the symmetries of the molecular states, and also, as we're going to see in this lecture, it helps us in simplifying the diagonalization of the Hamiltonian, because you can group different states with different symmetries in separate regions of the Hamiltonian matrix, and you can put your Hamiltonian matrix in a block form, in different blocks separated by zeros, and this allows us to simplify the problem of diagonalizing Hamiltonians. All right, so let me start with this very general concept of the equivalence, or the equivalence representation in group theory. We know that in a molecule, as in a solid, the potential energy for the electron is a totally symmetric function. Transforms according to the identity representation, and on top of that, you have atoms that are equivalent by symmetry, in the sense that when you apply symmetry operations on these atoms, they map one into each other, okay? And that leads us to the concept of the equivalence representation. So from a practical point of view, the equivalence representation is obtained by simply identifying the equivalent atoms in a molecule, and by, as I said before, by doing this map, by looking at which symmetry operations take one atom to another atom, okay? So in general, as we're going to see, the equivalence representation is a reducible representation. You can reduce it into irreducible representations of the group. We call it gamma AS, and we call it the characters of these representations, we call it chi AS, in which AS means atomic sites. So sometimes I'm going to call it atomic sites characters, okay, instead of equivalence characters or representation. So let's see how this works using as an example. Once again, the C3V group, the group of the equilateral triangle, in which we take, suppose a hypothetical molecule of this shape. It could also be the NH3 molecule. Suppose that I have three atoms, atom 1, 2, and 3. I'm simplifying using the C3V group. I'm ignoring the Z coordinate in this case. So how do I construct the equivalence representation in this case? So the recipe is to put the number 1 in a given IJ matrix element whenever the atom I is taken to the atom J, and put the number 0 in all other elements, okay? So how does that work? For instance, let's take the identity symmetry operation. So for the identity, atom 1 goes into atom 1, atom 2 goes into atom 2, atom 3 goes into atom 3, okay? So I have 1, 1, 2, 2, 3, 3. I put ones in the positions where atom I goes into atom J. So this is a trivial case. Let's see the C3 operation, rotation by 2 pi over 3, one of the two rotations of the C3 class. So in this case, I have a permutation. So 1 goes into 3, 3 goes into 2, 2 goes into 1. So 1 goes into 3, 3 goes into 2 goes into 1, and so this is the opposite, right? And sorry, 1 goes into 3, 2 goes into 1, and 3 goes into 2. So I'm rotating counterclockwise. So, and this is the matrix then I have to construct, and then I add zeros to all other matrix elements. So in this, for this operation, all the atoms are interchanged. But let's see now a sigma v operation. For instance, this mirror plane right here. For this mirror plane, 2 goes into 3 and 3 goes into 2, but 1 remains unchanged, right? So that's what I have here. 1 remains unchanged, and I swap 2 and 3. So that's the equivalence representation for matrix for this sigma, one of the sigma v operations. So you get the idea, right? So that's how you construct the equivalence representation. And also we can, from that representation, we can calculate the characters. So if you see immediately, the characters are the traces of those matrices. So you can see immediately that the characters are simply the number of atoms that remain unmoved or unchanged. Okay. So for the identity operation, the character is 3, right? Because all 3 atoms remain in the same position. So let me write here. Chi atomic sites, chi AS. It's equal to, in this case, for the identity is 3. For the C3 is 0, right? Because all this trace here is 0. And you can see that for both C3 operations, all the atoms are moving. So this is 0. And for sigma v, this is 1, right? So 1 atom each time it's unmoved by the 3 sigma v axis. So you notice already that this is a reducible representation because it's a 3 by 3 representation. And of course, the C3v group only allows the largest representation is 2-dimensional. So it's a reducible representation, but we can reduce it. We can reduce the equivalence representation, and you can immediately see that this is essentially, by looking at the characters, you see immediately that this is equal to A1 plus E, right? You just have to sum the characters. All right, so we have learned how to construct the equivalence representation, and it's reducible, and we already knew how we can reduce it to IRAPs, to irreducible representations of the group. But let's see why we are talking about that. I mean, what's the usefulness of the equivalence representation? Okay, so if you remember, the definition of the equivalence representation is reminiscent or reminds us of the ideas that we developed in chapter 4 about basis functions. If you remember, this equation is very similar to equation 4.1 in chapter 4. You can go back there and look it up. And basically it's telling me how, when I apply a symmetry operation of the group PR into a certain partner or basis functions psi I, and how this can be written as a linear combination of all partners psi j. And we have used this, and we developed the idea of projection operators in chapter 4, starting from this idea. But if you look now in the framework of the equivalence representation, you see that you're doing exactly the same thing. You just imagine the atomic positions as, let's say, s orbitals or little spheres, and psi I or psi j represent these spheres and the atomic position where they are located. And you can see that when I apply a symmetry operations to this set of positions, I get another position, and I don't get a linear combination, but just one position, because for each row or each column, this matrix, the equivalence representation matrix, has only one number 1. The others are all 0. Okay, so you can think of this as the matrix elements Rj of this symmetry operation, and you can imagine this, that you have this correspondence, right, between the atomic positions and basis functions that we have discussed last time. You just imagine psi I and psi j having the shape of an s orbital, for instance, and you have precisely this correspondence. Okay. All right. So that's what I have just said. This atoms acts like a s-like orbital basis, and and that's the idea. Decomposing this equivalence representation into irreducible representations, I have not shown that, but this is going to be precisely the same exercise we did in chapter 4. This will give us the possible linear combinations of s orbitals that transform like IRAPs of the group. So if you remember, we did that in chapter 4 for 3 s orbitals in a triangle, and if you remember, the result was precisely that. I could construct linear combinations of s orbitals that transformed like A1, the totally symmetric, or the identity representation is a symmetric combination of the 3 orbitals. And I could also construct a 2-dimensional representation E, right? But I could not construct an A2 representation, linear combination of s orbitals. But I did that in chapter 4 using, if you remember, the projection operators. So I'm here doing a similar thing with in a much simpler way, because I don't know yet what are the linear combinations, but I know precisely that I can only get A1 and E as the irreducible representations for this linear combination of s orbitals. Okay. All right. So, of course, to get the functions, the wave functions, I have to apply the projection operator sometimes, but it's very useful to know beforehand what are the IRAPs that I should expect for a given problem. Okay, so just to give you an example of how to construct the functions, the eigenstates, let me do this. I do this in this session 7.3, in which I discuss the idea of bonding and anti-bonding states. Bonding states or bonding combinations are also called direct valence bonding. And let me do a simplified diatomic homopolar molecule, which is described, the symmetries are described by the C1H group. So what do I mean by simplified? If you take a diatomic molecule like H2, this is for instance the H2 molecule, I have many symmetry operations, right? So this is a hydrogen atom, this is another hydrogen atom. I have many symmetry operations, and we're going to see that in a minute, because I have actually a semi-infinite group, because all possible rotations around this symmetry axis for any given angle is a symmetry operation of the group. And also you have an infinite number of sigma v reflections. But let's ignore this for a while, and let's consider this as a one-dimensional system. Okay, forget about the rotations and reflections, but let's say that I have a simplified set of operations here in which I only have two operations. For this C1H group, I have only the identity operation and the sigma H operation. So let me suppose for simplicity that the only two operations that I get are the identity and reflection with respect to a horizontal axis. Okay. All right. So this is the character table of the C1H group. I have two operations and two classes, and also two irreducible representations. There are two different notations for those. One could call them gamma 1 and gamma 1 prime, or A prime, A double prime, and the difference between those is this one is even under sigma H, and this one is odd under sigma H reflection. Okay. All right. So, and these are the atomic size characters. Okay. So when I apply the identity, both atoms remain unchanged, so the character is 2. And when I apply sigma H, they go into themselves, so the character is 0. And you can see immediately that this can be written as a sum of gamma 1 and gamma 1 prime. Okay, so this reducible representation is the sum of these two irreducible representations. All right. Now let's see how we can use now the projection operator that we introduced in chapter 4 to find the wave functions, of the bonding and anti-bonding combinations that will transform like gamma 1 and gamma 1 prime. From this analysis, I already know that the two solutions of the Schrödinger equation for this problem, when I have two S states, one solution will transform like gamma 1, symmetric, and the other will have gamma 1 prime symmetry, anti-symmetric with respect to reflection. Okay, so from the simple analysis, group theory already tells us that. So I can just use this formula of the projection operator, and let me apply the projection operator for the representation gamma 1, the symmetric one. And let's see, let's suppose I will call here atom A. So I have an s orbital here, and with this orbital I will call psi A, and on atom B I have another function, atomic orbital, that I will call psi B. So let me apply the projection operator to the function psi A using this formula. So this is 1/2, and then I have to the character of the identity is 1, and the application of the identity operation into psi A gives me psi A plus the character of the sigma h, which is also 1, and the application of the sigma h operation to psi a. Okay, and this is psi a, and this is psi b, right? So I get 1/2 psi a plus psi b. And you can already notice that this looks like a bonding orbital, right? The normalization is not right. One should get, if these orbitals are non-overlapping orbitals, one would get 1 over square root of 2, but I'm not really caring too much about normalization here. So let me do the similar thing for the gamma 1 prime representation. I'm applying it to psi b, and the result is 1, and this is gonna give me psi a plus, now it's -1, and this gives me psi b. So the result in this case, you can see immediately, it's 1/2 psi a minus psi b. And I can immediately recognize this as an anti-bonding combination of the atomic orbitals psi a and psi b. So, and you notice that I haven't solved the Schrödinger equation. I only used group theory. Okay, so group theory allowed me to find precisely the 2 eigenstates of this problem without even solving the Schrödinger equation or diagonalizing any matrix. So it's not going to be always like this, because this is a very simple problem, right? So it's not going to be always like that. But for this simple case, this is what happened. So and you can see right away. I will discuss this in a minute, but you see, this is a way to put. You can interpret this as a way to write the Hamiltonian into a block diagonal form. So I will discuss this in a minute in a more complete description of diatomic molecules. Okay. So so you're starting to see how the machinery of group theory works, and to simplify the solutions of different problems in quantum mechanics. All right? Okay, very good. So so let me discuss now in using full description of symmetries the case of diatomic molecules, and this is section 7.4, and I will start with the simpler case of homonuclear diatomic molecules. That means H2, N2, so on and so forth. Okay, both atoms are the same. Okay, so to discuss diatomic molecules, I have to introduce to you the concept of semi-infinite groups. What are those point groups? They, as I said before, they are point groups in which I have one symmetry axis and I have a complete rotation, full rotation symmetry around this axis. For any angle that I rotate, the molecule remains the same. All right? And I have two groups with with two semi-infinite groups in the case of the atomic molecule. The C infinite V group, that this is the case, for instance, for the CO molecule, which is not a homonuclear molecule, is a heteronuclear molecule. But for the homonuclear molecule, I have the D infinite H group. Okay? So what's the difference? The difference is that in one case I have inversion symmetry, and in this other case I don't have inversion symmetry. So if you use the ideas of direct product that I developed in the previous chapter, you can notice that D infinite H is the direct product of C infinite V with the inversion group. Okay? And this is so this is in general. So let me now go straight to the problem of homonuclear diatomic molecules, and let's consider again the H2 molecule, the hydrogen molecule, okay, with 2 s orbitals to start with. So in this case I have to deal with the D infinite H group. This is the character table of this group. These are the symmetry operations, identity. I have C phi, meaning the rotation for any angle phi with respect to the main symmetry axis of the molecule. Plus or minus phi are in the same class. And I have an infinite number of those operations. And I also have a C2 prime axis, rotation in a horizontal axis, and inversion and the combination of those. And this is sigma v reflection. So this is the chapter, the character table, and I have an infinite number of representations as well. For each value of phi, I have a different class. So I'm not showing, of course, all of them here, but it's a little bit. I think it's clear that I have an infinite number of classes, and for this reason, an infinite number of representations. Okay. Okay, very good. So I can start in a similar way I did in the previous slide by trying to write Chi-AS, the characters for the equivalence representations for this group. So once again I have to see for all these different symmetry operations how many atoms are invariant, how many atoms do not move. I have 2 atoms total, so for the identity is 2. For all C phi operations is also 2. But for the sigma, the C2 prime rotations is 0 because you take one atom to the other one. Inversion 0, and for the sigma v reflection, the character is also 2. So these are the characters of the equivalence representation, and again I can write immediately. I can notice that these representations is the sum of A1H and A2U. Okay, that in this other notation I can also call them sigma G plus, sigma U plus. G and U meaning even and odd under rotation. Under inversion, under inversion. And there's another index plus or minus indicating if the representation is even or odd under, let's see, under the C2 prime. Okay, there's another possible index of label of symmetry. Okay, but let's not care too much about them now. I'm just writing this to show you that I can decompose these irreducible representations into the sum of those 2 representations. Okay, so this is the equivalence representation decomposition. All right, very good. So, so by following precisely the same idea, this is basically the same as I did in the previous slide. I don't have to do it again, but I can immediately write down the 2 linear combinations sigma A1G, the bonding combination. I can also call it sigma S for symmetrical, as 1 square root of 2 sigma, sorry, psi A, not sigma, psi A plus psi B. This is the bonding state, and the anti-bonding state, psi A2U, or psi A for antisymmetric, is 1 over root 2 psi A minus psi B. This is the same exercise I could do using projection operator, but I already did that, so I'm not going to do that again. Okay, so these are the two eigenstates. So what I want to emphasize now is that the Hamiltonian, it's always diagonal in the eigenstate basis. So if IH is diagonal in this basis, meaning that, for instance, if I take off-diagonal elements such as this is 0. So I can write the Hamiltonian in a diagonal form. Big A, with elements symmetric and antisymmetric and 0, 0 here. So this is just to show you, as again, a simple example of how you can simplify your Hamiltonian, write your Hamiltonian in a block diagonal form without actually solving the problem, just using group theory. Okay, the powerfulness of this result is going to be more clear when I go to more complicated systems, and that's what I'm going to do now. But before that, I just want to show you a graph from a paper or a book, I don't know, in which I have here the energies of the electronic states of the hydrogen molecule. So this is the H2 molecule, and the energy of different electronic states as a function of the intermolecular distance. So I can, for instance, move these two hydrogen atoms closer to each other or far away from each other. I can change the R, the distance, the distance between the two atoms, and calculate the energy. So this is just to show you that if you see papers, you start to notice now that you can finally understand this notation, because this is simply group theory notation. You can see sigma G, sigma U. This is the bonding state for two s orbitals. This is the anti-bonding. This is higher energy orbitals, but we'll not care too much about them now. But again, you have the same notation there. You can see sigma G and sigma U that are precisely the group theory notation that you find in the character table. Okay. And also there's an extra label here, 1 and 3, and this is for spin. This is for specifying the spin state. 1 for singlet and 3 for triplet. So this is our example of how you interpret the notation, group theory notation in molecular states of molecules. All right, so let's do a more complicated case now, which is slightly more complicated. The heterogeneous diatomic molecule. So we have now as an example the CO molecule, carbon and oxygen. And the group in this case is the C infinite V group. Okay, it doesn't have inversion. And this is the character table for the C infinite V group. You have symmetry operations identity the infinite set of rotations around the main axis and the infinite set of sigma v planes. Okay? Alright. So the electronic configuration of carbon and oxygen is more complicated now. I don't have only s orbitals, but p orbitals start to be important now. Okay? So carbon is 1s2, 2s2, 2p2. Oxygen is 1s2, 2s2, 2p4. Let's ignore for a minute the 1s orbitals because they are much lower in energy. So they are not so important for understanding bonding, for instance. Okay, of course they are important, but let's ignore them for a while. And so we have to focus on s orbitals from the 2s atomic orbitals, and also p states that will come from the p xyz for carbon and px py pz for oxygen. So this is an interesting example because for the first time now we are going to deal with p states. Okay. So the first thing we need to do is to see the set of atomic orbitals s and p, how they transform according to the irreducible representations of the group. So in other words, they are basis functions for which irreducible representations of the group, and you can look it up in the character table. So the s orbital is a totally symmetric orbital, so it will transform like A1, the totally symmetric representation. But the p orbitals, px, py, pz, they transform like a vector, right? The p orbitals transform like a vector. So I have to look up in the character table where the x, y, z coordinates are. So I can see here x and y, and they are bases for the E1 representation. And I can see here z, which is a basis for the A1 representation. So the two pz orbitals, they will transform like A1, and the px, py orbitals for both carbon and oxygen, they will transform like E1. Okay? A two-dimensional representation E1. And of course the s orbitals transform like A1. Okay, very good. So what I need to do now is to calculate the characters of the equivalence representation. Okay, so the characters for the equivalence representation, once again let me call chi as, and when I apply the identity, both atoms do not change, and also for C phi and also for sigma v. So I have 2, 2, 2. So from this I recognize immediately that gamma atom sites is decomposed into 2A1. Okay? Twice the identity representation. That's the decomposition. Okay, so what is the next step now? So now this is, I'm telling you, it's a recipe, okay? I'm not explaining to you in more basic grounds, but I'm telling you what you have to do. What you have to do now is to construct the direct product between the equivalence representation and the vector representation. The vector representation is, as we've seen here, is the sum of A1 and E1. So I have to do this. 2A1 and direct product with A1 plus E1. And the result of these are going to be the possible irreducible representations of okay, so this is the case for sorry, I'm skipping the S case because it's similar to what we have seen, but this is for p states, for the p orbitals. Okay, for the p orbitals, this is what I have to do to construct the possible linear combinations of p orbitals that transform like the molecule. Okay, and this is easy to do. This is 2a1 plus 2e1. So the different a total of 6 p orbitals, right? 3 p orbitals from the oxygen and 3 p orbitals from the carbon. When they are far apart from each other, they are degenerate, but when I bring them close together and I break the degeneracy, they break into 2 doubly degenerate levels, 2e1 levels, and 2 non-degenerate levels, 2a1 levels. And from this, you see immediately that this is pz, right? And this is px and py. So this is going to be 2 pz molecular orbitals, and these are going to be 2 px py degenerate molecular orbitals. Okay, so this is for p orbitals. For s orbitals is the same. For s orbitals is the same as I have considered before. For s orbitals, I don't have to I can ignore the vector thing. So for s orbitals is simply 2a1. So I have 2 non-degenerate states, and of course you can see that one comes from carbon and the other comes from oxygen. Okay, so let me summarize all this information in a diagram like this that perhaps you have seen many times already. So what I see here is in the left I have carbon, and in the right I have oxygen. So these are not the same energy when the atoms are far apart from each other, because I mean the s orbital, the 2s orbital in carbon has a different energy than the 2s orbital in oxygen, but this is just a schematic. Don't worry too much about the absolute values of the energies here. So what this is telling me is that when I construct the CO molecule, the linear combinations that I will construct, I will form 2 linear combinations of s orbitals, but both transform like A1 representation, right? They are totally symmetric representations, but they are bonding and anti-bonding. So in one case I have C and O s orbitals plus and plus, right? So I build up charge here in the middle, and for the anti-bonding I have plus and minus s orbitals, and these are the 2s combinations that I get. Okay, so now let's look at the pz and pxy orbitals. For the let's look at the pz states first. So I have to combine a pz state from carbon and the pz state from oxygen in a bonding way. So the way to do this is working with the phases like this. This is a bonding combination of pz. So I use this choice of pz axis, And the anti-bonding combination, again a mixture of P Xy orbitals, now anti-symmetric one, is gonna be this minus plus minus plus. So I have a depletion of charge here in the interstitial region. Okay, so what about the PXPY? So PXPY for oxygen and for carbon, and I have, again, I formed two combinations, bonding and anti-bonding. I'm gonna draw here just for the let's call it the y-axis right here. The vertical axis, let me call y. And so the bonding combination of P Y orbitals is going to be something like that. Yes, I can do that better. This is the bonding combination of two PY orbitals, and this is the anti-bonding combination. The anti-bonding combination it's gonna be something like that. Okay, and the same for the PX. So for the PX, I'm gonna have exactly the same thing. Actually, I still, in the molecule, the PX and PY states, they remain degenerate, okay, because there is the symmetry between PX and PY when I rotate by 90 degrees. So that's why these two states are degenerate. So these are doubly degenerate states, bonding and anti-bonding, and the degeneracy is just PX PY degeneracy. One of the molecular orbitals I can write as a PX combination, and the other one as a PY combination. Okay, so you see that this is a more complicated example, but again, this is how far we can get from group theory. But now let me tell you how group theory can help us to simplify the Hamiltonian to be diagonalized. This was more like a problem in the old days when people didn't have much computer power. But still nowadays it's useful because it helps you to understand your results. When you know the symmetries of your states, and you can immediately identify the degeneracies and try to identify the spatial distribution of your orbitals. So this is less a practical problem nowadays, because with computer power nowadays you don't have to worry about decreasing the size of your Hamiltonian many times. But it's more like a tool to understand your results. Okay, so what is your Hamiltonian? Your Hamiltonian has it's an 8x8 Hamiltonian in Lcao, right? Because you have 4 orbitals from carbon and 4 orbitals from oxygen, because you have S and Px, Py, Pz for both carbon and oxygen. So I could, in principle, try to write the Hamiltonian matrix elements like this. Let's start with the carbon S orbital, and carbon Pz, and I will explain to you why I'm writing like this, and the carbon Px, carbon Py. This is a slightly random choice of ordering of atomic orbitals, and the same here for oxygen. This is oxygen S, oxygen Pz, and oxygen Px, oxygen Py. Okay, and the same order here for the rows. Okay, so these are carbon S, carbon Pz, carbon Px, carbon Py, oxygen S, oxygen Pz, oxygen Px, and oxygen Py. Okay, so what group theory tells us is I can block diagonalize the Hamiltonian according to the symmetries of the states. Okay, so I know before doing the calculation, I know that I will have a block in which I have A1 symmetry. This is the way the book writes this is not the best way, but I will show you in a minute how we can do it even better. But you can see this block, in this block here, I group S and Pz orbitals. And why do I do that? I do that because I know that S orbitals will I will make linear combinations of them in the molecule to make molecular states with the A1 symmetry, and the same happens for Pz orbitals. Okay, so I know beforehand that S and Pz, they will actually mix, they will hybridize when I solve the Schrödinger equation. So this picture shown here is actually approximate, because this molecular state, this A1 Pz, it can have a certain component of A1S as well, okay? Because S and Pz orbitals, they can mix and make also linear combinations. So group theory tells us that I have to treat S and Pz orbitals in the same block of your Hamiltonian, and that's why I have here the carbon S and carbon Pz in the same block, and they will interact in a sense with with oxygen S and oxygen Pz, which are here in this block. Okay, and I have another block here which is carbon Px Py, and another block here which is oxygen Px Py. And I also can notice here these matrix elements are non-zero, meaning that these two blocks are also going to mix. So this is telling me that probably to write your Hamiltonian in a block diagonal form, this is probably not the best choice of rows and columns. There is a better choice of rows and columns, which is the following. If I write carbon S and carbon Pz, and now oxygen S and oxygen Pz, I will construct a big block that I can call A1. This is all full of numbers here, and in principle non-zero, that I have to diagonalize then a 4x4 matrix to get all the possible A1 symmetry solutions of your Hamiltonian. And I can construct another big block here, which is carbon Px, carbon Py, oxygen Px, oxygen Py, because I know these will transform like E1. So I will have another block here full of numbers. This is the E1 block, with a bunch of numbers here, non-zero, and all the other elements are zero. This is a big zero, this is a big zero, all these elements are zero. So you can see right away now that I have greatly simplified my Hamiltonian by separating into I originally had a 8 by 8 Hamiltonian. Now I have two 4 by 4 Hamiltonians to diagonalize, and I know, before I do it, I know that I can label the solutions of my molecular states according to different symmetry. So in the end of the day, I will have 4 non-degenerate A1 states, and I will actually have two blocks, two doubly degenerate molecular states coming from this diagonalization. There's one extra thing actually that I could do, which is, let me write in another way here. Let me call this OPX, and let me call it, there's even a better way to do it. I can switch the order here, and I can call this carbon oxygen PX and this carbon PY oxygen PY. And I know also that X and Y are not going to mix in this problem. So actually this is going to be, oops. This is actually going to be 0. This and this. Because PX and PY solutions, they will decouple, and actually they will give you the degenerate states. So the bonding and anti-bonding PX are going to come from this block, and the bonding and anti-bonding PY, they will come from this block, but bonding PX and bonding PY will have the same energy, and this will make one of the E1 states. And anti-bonding PX, anti-bonding PY, they will also have the same energy, and this is the other block, E1. Alright, so very good. So I went as far as describing the diatomic molecules for the heteropolar case, and starting next lecture we will discuss electronic orbitals of multi-atomic molecules with more complicated groups, like the NH3 molecule and the CH4 molecule. So thank you, and the next lecture is going to be on Monday. Thank you very much, and have a good weekend.